Understanding how water is affected by wind and temperature is key to the hurricane model. As we've learned before, temperature, pressure, and volume are all directly related. As temperature increases, it creates differences in temperature between locations. Differences in pressure and wind acts to equalize them. Temperature also affects gas solubility potential, or the amount of air that can be absorbed by water over a period of time. As water depth increases, so does its gas solubility potential. On the western coast of Africa, trade winds generally come from the north. These trade winds are cooler and drier and have a cooling effect on the water below via the condensation effect. Water along the equator is heated more than anywhere else on Earth. This creates a low gas solubility potential at sunset, which increases until sunrise. The heating of water along the equator also contributes to an upwelling of deep water, which increases the gas solubility potential. The westerly winds from across the Sahara are arid and dusty. Arid air increases evaporation, thereby increasing the condensation effect along the coast. Also, dust in the air settles into the water, which increases the gas solubility along the coast. So a combination of condensation effect, increased suspension of dust particles, and an increase in evaporation due to arid conditions all contribute to a threefold increase in gas solubility along the coast of Africa. What does this mean? Well, the diffusion coefficient is used to determine the gas solubility potential. See, every mole of water has potential, and that potential is fixed to the variables explained above. But let's consider the true effect of that change in potential. A hurricane with a 50-mile radius has almost 51 trillion square centimeters of surface area, or the area where air and water meet. This is a minimum. Waves only increase this number. If the diffusion coefficient is 3 times 10 to the negative third, that correlates to 3.3 times 10 to the 12th cubic meters of air being drawn into the ocean every day under that hurricane. That's 3.3 trillion cubic meters of air. Gas solubility increases as depth increases. So keep in mind, as the surface water is increased, that potential remains as the gases are in equilibrium exchange with the water below. As gases are absorbed into the surface water, equilibrium causes those gases to transfer to deeper layers. Therefore, the potentials never reach homeostasis until the air conditions stop feeding that differential. For example, if the potential is 2 liters of air, that volume is the potential for the top layer, not the bottom. So it's like filling up a 2-liter bottle that has holes in it. So let's keep in mind all of these effects are stacked for an intense collective outcome. Trade winds blow south, cooling the water. As westerly, arid Saharan winds blow over, they further cool the water through a threefold effect: barometric, condensation, and suspension. The loaded increase in gas solubility potential causes a spiraling downward flow of gases throughout the atmosphere at immense quantities. Some of these effects exist daily throughout the world, but the combination of these effects merge and are amplified on the western coast of Africa.
Hurricane forecasters usually attribute hurricane formation to 2 factors, which are temperature and pressure. Our model describes the Saharan winds cooling the top layer of ocean, causing it to cool. This change in temperature causes change in maximum solubility potential described by Henry and Raoult's law. Change in the maximum potential of water in the ocean causes downward draft of the wind from atmosphere to re-establish gas equilibrium in the water because of gas displacement. This constant pull of air from atmosphere to water causes pressure changes, which eventually leads to hurricane systems.